So today's session is about Routh Hurwitz Criterion to determine the stability of sampled data systems. Let us have a quick look into the history of Rs Criterion. In 1876, an English mathematician Edward John Routh proposed Routh test to determine whether all the roots of the characteristic polynomial of a linear system have negative real parts. And almost during the same time, in 1895, at Germany, another mathematician, Adolf Hurwitz, proposed the Hurwitz matrix, in which the coefficients of the polynomial are arranged in the form of a square matrix, and showed that the polynomial is stable if and only if the sequence of determinants of its principal submatrices are positive. The two methods appear to be almost equivalent, with Routh test providing an efficient way to compute the Hurwitz determinant rather than computing them directly. But this requires a bilinear transformation mapping. And here the figure shows two planes, Z plane and W plane. W plane is a complex plane with alpha as its real axis and j beta as its imaginary axis. The bilinear transformation which is used for this case is Z is equal to W plus 1 by W minus 1. And if you consider a region inside the circle, unit circle in the Z plane, which we treat as a stable region, you substitute Z is equal to W plus 1 by W minus 1, and we can see that alpha is less than 0 in that case. This shows that the interior of the unit circle is mapped to the left half of the W plane. Similarly, if you consider the right half side of the W plane, you can see that it is mapped from the outside Z plane unit circle. Similarly, you can see that the unit circle itself is mapped to the imaginary axis of the W plane. Thus, by the bilinear transformation, we have P of Z transferred to P of W. Once P of W equal to 0 is obtained, the Routh Hurwitz criterion as applied to continuous time systems is applied here. The necessary conditions being all the coefficients of P of W equal to 0 should have the same sign, and also all the coefficients of P of W equal to 0 should be present. Now we consider the sufficient condition. Here we form a Routh table. The Routh table is formed with the coefficients of P of W equal to 0. So first of all we write W raised to 5 up to W raised to 0. Now you fill the Routh table with the coefficients. So we take alternate coefficients A5, A3, A1. Write that as the first row. Then for the second row corresponding to the coefficients of W raised to 4, we start with the coefficient of W raised to 4 itself. This is A4, A2 and A0. With that we complete all the elements of the first two rows, and by this time all the coefficients are also utilized here. Now we find W raised to 3. In order to find the first element of W raised to 3, we need to use some calculation. So B3 will be equal to A4 into A3 minus A5 into A2 by A4. Now we have B1 element. B1 is nothing but A4 into A1 minus A5 into A0 by A4. And C2 will be B3 into A2 minus A4 into B1 by B3. And C0 will be B3 into A0 minus A4 into 0 by B3. And similarly D1 will be equal to C2 into B1 minus B3 into C0 by C2, and E1 will be D1 into C0 minus C2 into 0 by D1. Likewise, we form the root table. Once you form the root table, you check whether the sign of the first column elements are same. It can be either all positive or all negative. If all the coefficients have the same sign, then we can say that the system is stable. Now we consider an example. Here P of Z is given like this, and you apply the bilinear transformation, we get an equation for P of W. Here the necessary conditions are satisfied, that is, all the coefficients of P of W are present and all the coefficients of P of W have the same sign. Now we form the root table as mentioned in the previous slide. So we have the root table. We can see that the first column elements are of the same sign. Hence the system is stable. We take another example, that is P of Z is equal to Z cube minus 1.7 Z square minus Z plus 0.8 equal to 0. We obtain P of W from a bilinear transformation Z equal to W plus 1 by W minus 1. We can see that the two elements have different signs. So the necessary condition is not satisfied and it is unstable. Even then, the root table is demonstrated here to show a special case. If you form the root table, you can see that the element corresponding to W raised to 1 will be like both the elements are zeros. So in this case, what we do is we consider one row prior to that. Form a polynomial with the coefficients 0.1 and minus 0.9. So 0.1 W square. Why it is W square? Because the row corresponds to W square. So start with W square. Then alternate element is W raised to 0. So 0.1 W square minus 0.9 W raised to 0. Take its derivative. We get 0.2 W minus 0. So these coefficients 0.2 and 0 can be used for the next row, that is W raised to 1, wherein we got both the elements as 0. So it is replaced by 0.2 and 0, and we continue the procedure. It is found that the first column will have one sign change. Since there is one sign change, the system is unstable. It is already proved that the system is unstable from the necessary condition. Thank you.